Hello, everyone. Now we are welcome our second speaker, Yutong Duan, from the University of Illinois at Chicago. And her talk is how to prove strong minimality of Lotka Volterra LV6 equation. Yutong, please go ahead.
Thanks for introducing and thanks for inviting me to this seminar. Basically, I wanna first introduce some background and definition of irreducibility and strong minimality, and then I can introduce the Lotka Volterra system of equations, and then I may go to what are the next questions we can ask. So for this talk and also for my research, I basically focus on the model theory. So there will be some model theory terms, but let me explain. So first, we have a definition. So if a differential equation y looks like that, and f is in C of x1 to xn, we say it is irreducible if for any differential field K, that is an extension of the complex field, and D is a derivative on that field, and any solution Y in a differential closed field, I will explain this term later, and usually we mean it is a monster model in model theory, and the transcendence degree is of y to the n-1th degree equals to 0, or equals to n. So that means either it has a generic solution or it has algebraic closed. It has a solution in the algebraic closure of K. And for as I just said, an ordinary differential field is a field with a derivation d from K to itself, such that d of x plus y equals d of x plus d of y, and also we have the Leibniz rule. And when we say an element in K is a constant, that means the derivative of it equals to 0. So for example, C joint T and with derivation d over dt is a differential field. And y double prime equals to y squared plus alpha is a differential polynomial, or say it is a differential equation, and also in model theory is a first order formula in this field. Okay, so you may recognize there are some mathematical logic or model theory terms like first order formula or something. So the next page is to explain the basic of the theory I'm talking about. So our language is contains plus, negative, multiplication, 0, 1, and the derivation. And we have the axiom as all the axiom of algebraic closed field of characteristic 0, and the rules for the derivation. And the fourth point is how we tell a theory, that is how we tell a differential field is a differential closed field. That is for any differential equations, let's say we pick two, f and g, with order of g that is less than the order of f, then there exists a solution f of x such that f of x equals to 0, but g of x is not equals to 0. So notice so for example, CT, the algebraic closure of CT is not a differential closed field, because if we consider y prime equals to y, then the solution, the generic solution of this equation is not in that field. And differential closed field means basically you have all the solutions of all differential equations in that field. So one important thing is every function field, is not a differential closed field. So why do we introduce this concept? Because first, you can kind of imagine there is a differential closure of a function field, and then based on that, in model theory, we can kind of construct a very good model that is a very good differential closed field, and satisfies good model theory properties. And we call this kind of model a monster model. And if we do research in this monster model, then everything will become kind of easier, and also it gives us some very important results in model theory. Okay. So first is notice DCF is what I just defined. So the theory of differential closed field, and usually, although I didn't write DCF underscore 0, but we just assume the characteristic of the field is 0. And in model theory, DCF is a complete term theory. By term, I mean it has a lot of good properties. For example, it has quantifier elimination. Sorry for the upper course Q, case Q. But if you guys are familiar with model theory, you may know what this means. But if not, I can explain later. So, and also it has elimination of imaginaries, and it's an omega stable theory. And but compared to ACF0, that is algebraically closed field of characteristic 0, it is not a strongly minimal theory. So what do I mean by strongly minimal? So first, let's look at just a definable set. That is, or say a set that is defined by a formula. And a formula means you just use all the symbols I just defined to write a first order, to write some sentence, some formula. So formula means it contains free variables. So with that free variables, you can look. So all the points that is in the model and satisfy this formula gives you a set. And this is we call this a definable set. And we say a definable set is strongly minimal if all the definable subsets in it are either finite or cofinite. And a theory is strongly minimal means all the definable sets in that theory is strongly minimal. And so notice ACF0 is a strongly minimal theory, but in DCF0 it's not. So for example, y prime equals to y. I mean, I will give an example in 1 minute. Yeah, and also there's a very remarkable kind of good result, that is irreducibility is equivalent to strong minimality in DCF. And also you can use terms, you can use concepts and theorems in model theory to prove this result. And so in this talk, irreducibility is just a strongly minimal. So when you see that word afterwards, then you just know what does it mean. Okay, so why we do research on strong minimality? So several reasons. First is there is a very powerful theorem in model theory that so that once one can show some equation is strongly minimal, then you can apply this theorem and then do more study on the relations of solutions. And this theorem is a trichotomy theorem. So I didn't put on this slide here because it contains a lot of model theory terms. But basically what saying is just you can split into 3 cases. First is your definable set is like a field. And second is your definable set is like a group. And third is it's just a set and no structure on it. So that means it's really hard to use one solution to find another solution in this kind of set. And notice irreducibility also means so you cannot find a solution in classical way. For example, you there's no algebraic solution, and also there's no solution that you can take first integral or something. Yeah, and so that means for this kind of equation, it's really hard to find solutions. And also, there's another reason that for those equations with only constant parameters, if you have strongly minimality, then you have geometric triviality. So geometric triviality means if any two solutions is independent over your differential field K, and then any n solutions are independent. So it's also kind of a strong theorem. And I can show you some existing results using both algebraic way and mode theory to prove. So there are some Panevet equations. I didn't put the sixth Panevet equation because there's no enough space. But you can see Panevet equations are kind of it's not easy to find solution in Panevet equation, and it's kind of complicated. So at first, in 1987, Umamura proved the first Panevet equation is irreducible in an algebraic way, or I think he also used the group theory. And then in 1997, he also proved the irreducibility for second Panevet equation with alpha is not in 1/2 plus z. So if we look back, you can see the second line, which is the second Panevet equation, has a parameter alpha here. So whether it's irreducible is depend on the value of alpha. So and from the point 2, the subpoint 2 of point 2, you can see there is a subvariety of the second Panevet equation, and that's why we don't have strongly minimal of the DCF theory, because you can find an infinite solution set in Panevet 2 equation when alpha is in 1/2 plus z. And then at 2017, Negro and Pili proved that all generic Panevet equations are strongly minimal and geometrically trivial. And in this one, they used the model theory. So if just for strong minimality, the results are better. Just as you can see in Panevet 2. So only thing that is not irreducible is when alpha in 1/2 plus z. But for generic, we mean, so the parameters alpha, beta, so you can see in the previous, so there are parameters alpha, beta, and in Panevet 3, alpha, beta, gamma, delta. So if you have several parameters, just to look at the parameters in space C to the number of your parameter, then generic Panevet solution equations just mean you have those parameters are generic points. So that's some result I'm gonna talk. And also, not only you can prove Panevet equations strong minimality, you can prove that in Schwarzian equation and also Poisson equation. And what I did is about the Lotka Volterra equation. So the reason, first reason is it is not just an equation, it's also picture predator premodel. And also, if we add some other variations, you can have like x prime equals to x times a minus cx but minus by, y prime equals to minus y times d minus ex minus h. So I think here x denotes the number of prey, and y denotes the number. X is predator. X is prey and y is predator. So but here in the in this model, we have several constraints about A, B, C, D, E, H. But in math, we can generalize the conditions. So what I really looking at is this equation. We only have 4 parameters, B, C, and capital A, capital B, with all those parameters not equals to 0, and all of this in complex number, and little b or capital B is not in the it's not rational number. And so why the reason I that's not like this to be rational number is that this condition will be used in my proof, and I haven't proved the strong minimality that when it's in rational number. So I mean, there is a potential that it is strong minimality, but we haven't proved yet. So as you can see, I'm using model theory way. So let phi of xy. So this symbol means the only free variable in my formula is x and y. So let phi xy denote this system of equation. And then let theta x says that phi xy and not y prime equals 0 and x prime equals x, and not x prime equals 0 and y prime equals by squared, and also xy is not this. So the reason is we only want to look at the generic solution of the Lotka Volterra system of equation. If you model fit in those one subvarieties, then you can just look at the one subvariety equation. So yeah, and then my main theorem is theta of x is a strongly minimal set in theory DCF0. Oh, by the way, so maybe you are wondering why I just write theta x instead of theta xy, because you can express y by x and x prime just using the first equation. So basically, you just need to add this equation to your formula, and then theta x still tells you that x and x prime, or x and y, which is defined by x and x prime, is a set of solution to system of equations 3. So the main theorem is theta x is a strongly minimal set in theory DCF0. And here's my proof. I prove by contradiction. And I denote this courtesy to be quadrant B, C, A, B, all the parameters, and then take the algebraic closure. So first I have 2 claims. First is assume theta x is not strongly minimal. Then let differential field K and solution XY is witness. So remember, in the irreducibility, we need to have the transcendence degree K during the solution, and then over K is 0 or 2 in our case. And so we need to have, so by witness, we need to have a differential field K and a solution. And here, so because I assume it's not strongly minimal, that means the transcendence degree can happen to be 1. Okay, and then the claim says, then there exists A that is not equals to 0, but is in the algebraic closure of K, such that A is a solution of the equation A prime equals to CA. And you can imagine from here that there's no, I mean, the witness differential field K cannot be C or CT out. And what's more, if you know those concepts in model theory, theta of x isolate its generic type P over constant C, because basically because we don't have sub-1 variety. I mean, so all the order 1 equations over C cannot be a subset of this formula, and the non-minimality degree of P is 1. So claim 2 is for the same A, we have the first field C joint XA and then take algebraic closure equals to the algebraic closure of C joint XY. That means, so basically if the transcendence of these two fields are the same, and also these fields are differential fields. Okay, now we can finish our proof. So because we have y in C joint XAL, that means we can have a Puser series expansion of y0. And then I can plug in this expansion to the first equation, and then I can compare the parameters before some term. And you can see those are all contradictions for those three cases. So that means we cannot have the theta x to be, that means we need to have theta x to be strongly minimal. Okay, so, and as you recognize, so the equation 3 is in fact over constant. So that means it is automatically geometrically trivial. And then next questions to ask is about the relations of solutions. So for example, if xy and uv are two solutions, can we have xy in the algebraic closure of C joint uv? That means, can we use polynomials to find another solution? And also, furthermore, do we have just the x in C of u out? And in model theory, this means strong triviality. And also, how many solutions can you find? Just using one solution. That it means how many solutions is in the algebraic closure of C joint xy. If it is finite, we call the equation is omega categorical. And if it's just one, so that means xy is the only solution in its algebraic closure, then we say the equation is strict disintegratedness. And all of these questions haven't been finished, but I'm kind of working on that. Yeah, and I think that is my talk for today.